Welcome and thank you all for giving us the opportunity to come share with you the results from our project, which was automated helicopter flight control. My name is Angela Nakalembe and I'm together with Caleb Clark and Bonham Griggs, and combined we have over 9 years experience in chemical engineering and programming, which we believe made us more than ready to take on this task.
We understand that some of you may have concerns about relegating control of a machine as complex as a helicopter to nothing more than a computer, but we're here today to put those concerns at rest.
The objective of our study is to control the takeoff, mid-flight altitude, and the landing procedure of a helicopter. And this was done in a Python simulator and with a PID controller. Our model used a momentum balance which summed the forces of the helicopter in the vertical direction. This includes lift, drag, and gravity. We focused on altitude control and neglected all horizontal forces. The size of the disk created by blade rotation was used for the helicopter area for our drag calculations. Helicopter flight is complex. In developing our model, we needed to implement coefficient of drag values that were 100% greater than the coefficient of drag values encountered in our literature review in order to create a smoother model and smoother control. Overall, we are pleased with our model and the performance of our controller.
Okay, so let's see how our helicopter did. There it is, getting ready to take off, and it is climbing up to its first set point at 4,500 meters. There it goes, descending down. You can see a few of those little oscillations there, and it is going in for a safe and smooth landing. There it is. Okay. So you'll notice that we set a minimum throttle of 50%, which isn't enough by itself to overcome the force of gravity, but helps to prevent the chopper from going into a state of free fall, which would be pretty scary for the pilot and any passengers. And our controller stays very close to its set points, but small oscillations remain once it gets there. We tried very hard to eliminate these oscillations, but we believe that they can only be totally eliminated with a significantly more complex model. Nevertheless, we were very proud of our overshoot ratio and our peak time and decay ratio, which are all very small.
All in all, with our user-friendly Python code that employs tuning parameters that we can easily change, we were able to successfully control our helicopter's takeoff, flight, and the landing, especially by controlling the throttle, which ensured a slow, safe landing velocity of approximately 2 miles per hour. And so for further study, we would recommend implementing a more complex model that would investigate the potential second-order nature of this system, as well as include the horizontal component of the system. Finally, attached is a copy of the previous team's video, which inspired us to pursue this project and can be used to compare and see the value that we have added to this ongoing project. So thank you so much for listening in, and leave any questions in the comments